大家好，我是 Charly，我是巴西人。But all my Chinese goes by. Sorry about that. I would love to deliver the speech in Chinese as I'm in China, but my Chinese is still an improvement. So today we're going to talk about reducing cost and improving performance. Those two things, they look very different. So when you're talking about improving performance, usually people are going to tell you to buy more hardware, put more memory, put more CPU, or get better hardware, right? So usually those are how things go by when we are talking about performance improvement. So I'm going to do a short introduction about myself. The talk is not about myself, but I have more than 20 years working with database. I'm a Brazilian, so I basically work between Brazil and China. Well, not necessarily between Brazil and China. Sometimes I spend some time in Brazil and sometimes in China. So, but what is this talk about? What are we going to talk today? The first things we're going to do is we're going to have a short overview. We're going to talk about heap files. So, what is heap files? It's something that we can eat, something that we can use. We're going to talk about padding and how much that's going to cost. And by the end, we're going to have a short summary. Right? So, let's start with a short overview. This is basically what we're going to talk today. You can see here, this is a summary of our talk. Except that we're not going to talk too much about free space and vacuum because we have a short amount of time. So we're going to try to cover how Postgres works internally with the data and how we can use that knowledge to improve the performance and how we can use that knowledge actually to save some cost, save some money. All right, first things first, let's try to get on the same page here. So the first couple of slides, they're very basic, especially if you're coming from a computer science. So you should know how those things work. And this we're talking about basically computer architecture. When we talk about computer and microcontrollers and microprocessors, they basically can do two things. They can do I/O, and they can move bytes internally. When we're talking about I/O, usually people think only about disk. So actually I/O is everything. Everything that comes from your memory card, everything that goes into your networking, everything is I/O. And this is basically what CPU can do. The CPU can only move bits from one place to another place. And moving those bits, it does the magic. But one thing that usually people forget is I/O. Different types of I/Os has different type of costs and different types of performance. If you see here, on the base of this pyramid, we have our auxiliary memory. So usually that's nowadays are SSDs and NVMEs, but used to be before on spinning disks. The spinning disks, they were kind of interesting because depending on how you save your data, they could work much faster or much slower. So if we work our data sequentially, that would be much nicer to both write and read. Sequentially means one after another. So you have here all the data sequentially, so that would be much faster. When it comes to solid state drivers or SSDs and NVMEs, we still have some performance difference. So if we can put all the bytes together, closer to each other, we can still have some improvements. And then we go to the RAM, the main memory. So RAM is more expensive than the auxiliary memory, but for the other hand, it's much faster. If we go up to the pyramid, we go to the cache and then the register. So if you're a game player, when you buy your hardware, you usually check the CPU, how much cache that CPU has. Because the more cache, the faster your CPU is going to operate, and the the more resolution and faster you can get your game running. And that also works for other applications. And cache is an important expression here. Keep that expression in memory because we're going to talk a lot about that one. So one thing that happens is the CPU, which is the fast thing in your computer, it does not have directly access to the secondary memory. So it means it does not have directly physical access to your SSD. If the CPU needs anything to work that is on disk, it needs to ask the memory. So the memory has a physical controller that can get the data from the disk. And this operation is slow. So the more data you need from the disk, the data needs to go from the disk to the memory, and then from the memory to the CPU cache, and the CPU cache for the register, where actually the work is done. So if we go back here, this is where the CPU works. All the work is done into the register. The register has access to the cache. But the cache does not have access to the disk. It only has access to the memory. So that's why we always try to keep data into the cache. So, but you have different levels in different types of caches, right? The RAM can still be a cache. And we usually think that the RAM is really fast, and we always try to keep more data in RAM because we're caching data from the disk. But the thing is, RAM is still much, much slower than the CPU itself and the CPU cache itself. So, but how those things can work together? How can we do things together? One very basic concept that we need to understand is CPU works with blocks. CPU does not, memory actually works with blocks. When we get information from the memory or when we get information from the disk, you usually don't get 1 byte or a few bytes of information each time. Every time that we need to get data from your SSD, it will get a block of data, a package of data. And the most common block size is 4 kilobytes. You can change. You can go for your OS and change the block size. And you can even see what is the architecture of your hard drive to see what's the block size of your hard drive. And you can align the block size of your hard drive with the full block size of your operational system. Alignment is another word and expression that's very important here, and that's going to play along. So alignment means if your hardware, if your SSD has a block size of 4 kilobytes, the best block size that's going to work for your OS is 4 kilobytes. Because every instruction, every time that needs to get some data from the SSD, it will always get exactly 1 block size. So, but what is the problem with misalignment? Well, we'll see soon. But now, before we go about misalignment, let's talk about heap files. So, when we work with databases, there are a few different types of organization of files that we can work with the database. We can work with heap files, or we can work with indexes files. So, a very important concept on the heap files is that the heap files doesn't keep any order. So, when we set data on your database, especially in PostgreSQL, it will not guarantee any order that we're inserting. Actually, the order is the order that we're inserting now. So let's say you insert 1,000 records, and you have an ID that goes from 1, 2, 3, 4, 5, up to the 1,000. So if you check the data file, you see those IDs quite clear in the order of 1, 2, 3, 4, just like you inserted. But what happens if you do an update? So the way PostgreSQL works is a little bit tricky. When you do update, let's say I want to update the name of the user ID 5 to Charlie, the database will read that block, will get that row ID 5, We'll change the name to Charlie, and then it will save on the next available free space. It can be on the same block, if the same block has free space available. But if the same block does not have free space available, it will save that data on the next block, or on the last block that has an available space that we can save that information. So this is why when you do a lot of updates on your database and you do a select without order by, it comes randomly result. And that's why an order by is very important, because now you're telling the database, okay, I don't care how it's organized internally, but I want to show and see the data in this very specific order, right? So it has a lot of advantages, which is, if you're going to read the data, you can just read sequentially the data. Remember that sequential reads are much faster on disk. So when you do a full table scan on PostgreSQL, that's highly efficient because it reads the data one block after another block. So that's the best way to read the data. But what happens when you have an index and we need to read the data based on an index? Well, that's going to change from a sequential scan from an order on disk. So it needs now to get the blocks. As we see here, an index has a tree-based data structure. So it means that the next block from the index is not necessarily the next block on the disk physically. So you may jump from one block to another block. Maybe the next block in the disk is this one because that's what was inserted first. So now you go in a random order in the disk physically, and that's more expensive. Another problem is Postgres does not have, the data is not ordered by the index. So physically ordered by the index, it means that needs to go to the index first, and if you need a data that's not in the index, it still needs to go to the data files. So every time that you do an index scan on PostgreSQL, we're changing from a sequential to a random order. Another important aspect is that PostgreSQL organizes everything in blocks as well. So it's usually common naming pages, but we can interchange the naming pages and blocks. They're basically the same thing. Just a second for some water. So, but the pages on PostgreSQL, they don't have 4 kilobytes. They actually have 8 kilobyte size. So it means one PostgreSQL page is usually 2 blocks in the disk. That's not a problem by itself, but that's okay. So, but how is it organized internally? So when we open a page internally on PostgreSQL and I do a scan, this is basically what we see. So in the beginning of the page, we have a header. The header has a lot of descriptors. It will tell how many rows we have in that page, what are the size and everything. So, and the funny thing is, Postgres holds all these pointers here in the beginning of the page that they don't have the data itself. Actually, the data on the PostgreSQL page, they start from the end of the page. So the more data we set on that page, it will put in on top of the previous data. And we have those indexes here, those pointers actually, that they point to the data itself. It's interesting because if we have an index, well, ignore the arrows. I asked the AI to create this diagram, and the AI is not capable to put the right arrows here. And no matter how many I asked to do. But anyways, so when we have an index, the index will point not to the data itself. The index will point to the pointer here. And why does it matter? So let's say, for example, this page, see, we have a lot of free space here on this page. If I do an update on this data here, let's say I want to update the name from Charlie to John, this row, remember that I said this row here will not be updated in place. What Postgres does is will mark this data as deleted, as removed, will copy the data, change the name, and save the data on the free space. Now we have 2 data spaces with information here. And it will change, update the pointer here for the next one. This trick means we don't need to change the index. We don't need to update the index because the index is pointer here, not here. So PostgreSQL will follow the index will point to the line pointer will point to actually the data. So in this case, we don't need to update an index. This is what PostgreSQL call hot. So the hot or heap only tuples updates, this is how it happens. So a trick that we can do is we can always allow some free space. There is a parameter in PostgreSQL that's the fulfill information that you can leave some space here. So if you have a lot of updates, you don't need to update the index every time if you have some free space there. So this is a trick. This is how we can start improving performance here. But, well, we said we're going to save data, save costs, right? So this is still not saving costs. And the costing things on our talk comes to this thing here. Can you see a problem here? Anybody? If nobody wants to answer, I'm going to point someone. So this is a very simple data structure. We have an ID that is an integer. We have a Boolean is active. We have an integer for the score. And we have a long for updated value. That could be a game, for example. If you have a game and want some information on a game, that's something very common. Can you see a problem here? It looks normal, right? Actually, it will compile. It will work. But the problem here is, remember what I was saying about alignment. So when we go to the CPU and memory, the CPU and memory, they will always try to work with alignment. So every single CPU has what they call word size, or how the size of the CPU can fit in the cache. Remember on the registers that we were talking about. So every cache has a line, a cache line. So let's go back to the beginning here. So every one of these cache has one line, let's say one of this thing, and this line is the size of the CPU word. If you're working with a 64-bit CPU or 8-byte CPU, this is the size of the cache line. It's 64 bits or 8 bytes. This is important to understand and to know because every time that you save, let's say, one of these data here, this data has a size. An integer, in my example, it's going to have a size of 4 bytes. A Boolean has a size of 1 byte. So we have 4 plus 1, 5 bytes. We have another 1 byte here, 6 bytes. And we have a long that has a size of 8 bytes. So if you sum up, it's 8 plus 4, 12, plus 1, 13, plus 5, 17 bytes, right? So this is the size what we're going to occupy in memory. But the problem is, the CPU doesn't split the cache line. So in this case, we have 4 bytes plus 1, it's 5. So it's missing 3 bytes to have a cache line. But now I'm putting on 4. This one cannot be together. Those two are going to be on the same cache line, and this one goes to the next cache line. And then we're going to have 3 bytes here that's just empty, or padding. This is what the padding does. So instead, we're going to have 8 bytes plus 8 bytes, because this one is 4, but the next one is 8, so they cannot stay together. 8 plus 8, 16 plus 8, 24 bytes. See, we have a waste of 7 bytes here in this small example. And let's say you have 1,000,000 rows with this one. It's 7 bytes multiplied by 1,000,000. This waste goes to your disk, and also goes to your memory, and then goes to the CPU. So more CPU cycles. It means you're wasting performance just because you didn't organize well your data structure. And this works on the database as well. So Postgres tries to follow those rules. The data in Postgres, every single data type, has a specific size. And that specific size means it has its own alignment. So if I work with integer, if I work with double, those kind of stuff, they have this specific alignment. And means that when we save the data, when you create your table, you do a create table, we're going to see a create table soon, and let's say you put some data here, and if it does not have the alignment, it needs to put a padding. And the padding is between the columns. So, and this is how those things, they work together. So, to make things faster, for the CPU not to do extra work, we do the padding. And let's get an example here. I have 2 tables. So the first table here is not well organized. So they are the same table. They have the same items. The only difference is that I reorganized the second one to be in a better organization for the type. So we try to avoid padding. And the first one, I put in a way that we can have the most padding possible for this example here. So if we check the data types, the first one we have an integer of 2, that's 2 bytes. Another integer, but now an 8 bytes. A boolean, another 8 bytes. A numeric, and an integer of 8 bytes. So between those integer of 8 bytes, we cannot have anything together to them. So if I have 2 bytes, and then I cannot put extra 8, so I have 6 bytes padding there. I'm losing 6 bytes. Here, this is 1 byte. From this to another one, I'm losing another 7 bytes. So in this small example, if we check the database, the first one, I inserted 1,000,000 rows. The first one is 73 megabytes on disk. The second one is 58 megabytes on disk. And the more I insert, so a few million rows more, the difference increases. But also increases proportionally, because it's a linear difference that we have here. And this is when we start saving data. If we go back to the table, look, it only has 1, 2, 3, 4, 5, 6 columns here on my table. It's a very small and a very simple table. Imagine your application that you have hundreds of tables. Some tables might have hundreds of rows. The impact that it has on disk. And now this is money. So your data provider, your cloud provider, they don't care if you don't know that you're paying for empty space. They're going to charge you, even for that waste of space here. But keep in memory, everything that we put on disk also goes to the CPU and goes to the memory. So the same waste of space that we have here, the same padding that we have here, things are scaling, things are growing here, we're going to have a performance issue that also going to give us a performance problems. So every time that you insert a row, instead of inserting a smaller amount of data, now we're inserting more. So, and the disk doesn't care if we're putting something empty there or if we're writing actually data, because it still needs to allocate that space on disk. So that gives us a performance problem as well. I'm missing. Yeah, I'm missing a slide here. But let's talk about this a little bit more. So in some tests that I did, I got here a 26% performance difference from this table, inserting on this table, other than inserting on that one. So there is 26% slowness because I have too much padding. So I'm paying the performance price here to insert data just because we're wasting space. And I also had around 17% read performance difference between them. So those numbers, they mean that you can have less disk, you can have less CPU, and you can have less memory. Working in a more organized fashion, working on a way that you eliminate the padding, that you put the data types or in an organized way, it will save a lot of money. So here we are talking about 20–25% savings. So it means that you can invest in something else. You can save more data. You can make your application faster with the same money. And what are the summary? What did you learn today? What did you see today? So PostgreSQL, it does use heap files. That's good. But also has its own disadvantages. As I said, the data is not organized on disk. And depending how you save your data, and depending how you create your indexes as well, you can have actually issues. Have you ever thought, why didn't the database choose the index that I created here? Sometimes you create a table, you create a nice index, and then the database starts using that index, and eventually the index is not used anymore. And then it goes for full table scan. Because when we come back, we go back here, we'll see that the database needs to read the index, and remember the index it organizes in a tree fashion, so that means random reads. So when you use an index, the database will change a sequential scan to a random scan on disk, which is more expensive. And then after that one, it still needs, depending on the data, goes to your data type and get the data. So a lesson that we can take from here is, if you can create a covered index, but what is a covered index? An index that has all the data that you need to fulfill the select. For example, if I always search for ID to get a name, and I create an index with ID and name, all the data that I need for that select is on the index. The index solves my select. So those are the tricks that we need to understand to also get some performance improvement. So the files are divided in blocks. So the data has no order, so the updates, you cannot guarantee the order that you create your tables. The insert is not necessarily going to give the order, because if you do updates on your table, so the order might change physically. Deleting a record does not mean that it's physically removed. Actually, it's marked as removed, just like the update they did that we show. And every data type has its alignment requirement. And depending on the alignment requirement and how we organize the data type, we are at padding. And this is what we need to learn for today. And padding is really, really, really bad. So if you can organize your tables, your data model, you don't need to change anything on your application. Because most of the applications, and they don't care about the order of the columns on your table. So you do a select, name and select ID, name, or whatever. This is what the select does. It doesn't matter if you change the order, if the first one that comes is not ID, if it's name. So for the application, it doesn't really matter. But for performance, it does. Padding is a really bad thing. One thing that you can learn today, and you can keep in memory, is padding is bad. Try to avoid it. Try to always keep clean and well-organized the data that you have. So that's what we have for today. We have here contact information if you want to keep in contact. That's all. If you have questions, we are open for questions.